If you're ready on this one, I'm going to take you a journey on the math equations so that we can get Planck's constant distribution, which matches black body radiation, which is where the idea for quantum mechanics came from. If you're not mathematical, I don't really suggest you sitting here and going through this. This is a way that I can record all these different facts and figures. So each one of the screens that follows this is going to have some math equations and questions that are asked about that and how we eventually get to the beginning. It's going to go all the way back to probability theory and then finally lead up to the equations that, well, like I said, Max Planck. Anyway, that's my introduction. So I don't want to bore you if you don't want to see the math. All right, let's take a look at this thing right here. This is a equation with lots of symbols to it. Let's look at what's here. We have talked about Planck's constant. We have talked about, have we talked about Boltzmann's constant? Maybe not. We'll have to investigate that. We've talked about absolute temperature, certainly when we were talking about the peak levels that Wien's relationship showed us. We haven't really discussed why in the heck c cubed would be down here. C cubed is speed of light cubed. 8 pi, what's that doing there? And this looking thing looking like velocity, but it's not. This is really frequency that we're talking about. Talking about frequency, which is this Greek letter nu. So instead of F, if you want to look at this thing nu and consider it as frequency, that probably would help you out a lot. But anyway, here's frequency. So certainly the HV, Max Planck's constant, and nu, which is frequency, there's an energy. There's an energy level. Now the rest of this, where do we start? Where do we start with trying to understand what all this is about? Well, let's go back a little bit and try and figure out what's going to happen next. Which thing do we want to tackle first? Do we want to tackle this thing first? Or do we want to tackle this thing first? Which thing do we tackle first? I think it's probably easiest if we can figure out what all this garbage is all about. So we'll concentrate on that one next. Okay, here's that piece that we were trying to look at in the last screen. Where does this all come about? This is a law that doesn't have Max Planck's constant in it. It's got the energy. So this is going to give the energy of the black body radiation for a specific frequency. And in place of Planck's constant, all we have is this K, which happens to be Boltzmann's constant. Just put a B there for Boltzmann. And T is temperature, C is the speed of light. Again, we still don't know what in the heck the speed of light is doing there. and this is the frequency squared. So this is the next step. So where do we go next from here? Let's see. Shall we try and figure out what the 8 pi frequency squared over speed of light squared is? Let's see what the next step is from this. This looks familiar. This is the number of states that a frequency mode can occupy. This one says per unit volume, and this one says the total frequency. This is per unit volume. This is not. So which volume are we talking about? Which volume does this thing come from? Here's L cubed. L cubed. L cubed what? What are we cubing? L is the length of a box. In 3 dimensions, we can consider this a box, and this L is representative of the length of that box. So that's where this volume thing down here comes from, the length of the box. Now, what in the heck is this K thing all about? Here we have the differential of n, which is the number of states, and now we put it in terms of this K. What is K? Why are we talking about K there? Now in this one, we're going backwards. It's kind of a strange way to do this, but we're going backwards and we're saying 4 pi p squared. What is 4 pi p squared? That happens to be the area of a sphere. Four pi p squared. So what is p? P is the radius of that sphere, and dp is the differential of that sphere for one small change, one change of frequency mode, and that's going to give you the volume. That's going to give you a volume. Volume, volume, volume. L cubed, that's the volume. And so it becomes a volume down here as well. So that's what's going on. That's where this 4 pi squared or 8 pi cubed thing comes along here. So let's go further and see if we can make sense of this. Let's start with this. K squared. Each one of these k's equals pi over L. Well, L, that's a big deal. That's the length of a box that these waves could be vibrating in. And each one of these L's is an integer for each one of these different k values, which is either an x, a y, or a z component. Somehow we wrap all that stuff around, and instead of saying k squared, we call it p, which has a vector. Now let's see if I can make some more sense of that. Here's p, and each one of these lengths is the k dimension. Here's a k dimension in the x dimension. Here's an m for the y dimension of k. And The z dimension you can't see because we're just on a two-dimensional page, and that would be going either into or out of, let's call it, let's see, that would be into the page here at this 0 origin. Anyway, here's this p thing that's being discussed. And that p thing is going to identify each one of the frequency modes that's occurring. And if you look at this sphere here, if you look at that sphere, the area of that is going to be 4 pi p squared, because p is the radius, and dp is the incremental change from one p to the other p. Each p is separated by about square root of 3, but let's just think of it as each one of the k dimensions is incrementing by 1. So that's going to be the incremental volume. Each one of these volumes is going to be the only number of modes that can occur. Now, why am I saying the only number of modes that can occur? Well, we're going to have to go backwards a little bit to understand that. Consider a cubical box of side L. Why are we doing it this way? Well, we have to start somewhere, and we just imagine that there's any box. It doesn't matter what the L dimension is, any box will work. And then we have the wavelengths of, let's see, if they say the standing waves, conducting walls, the electric field can only fit waves into the box which are multiples of half a wavelength. So no matter what L we choose, this is going to be the lowest frequency that will fit in there, half a wavelength. This is a full wavelength. This is 3 wavelengths. Now, if you looked at some of my other videos, I went over this as well. But where are we going with this? Why are we doing all this? Well, it started out that we needed to know the frequency modes, the number of frequency modes that could occur before we could figure out what the total energy would be. Not just a single frequency in one dimension, but it's got to go in 3 dimensions. Here we are counting the number of modes still. Now the 1/8 means that we only include the positive directions for each one of those p's that I showed in that back diagram. So we only include 1/8 because there's a x positive, y positive, and z positive, and that will only give us 1/8 of a sphere. So we got 1/8 of a sphere. Now, what happens down here? Well, remember those p's, each one of those p's was composed of kx, ky, and kz. So if we go back and include the ideas of the k, each one of those k's is pi times p over L. So we, in place of this p, we start fitting in these k's. What do we need the k's for? That's so we can have this L dimension in here. So we can have the volume of this thing. Okay, 4 pi frequency times this volume, that L squared. See, some weird things happened here. We got volume in there and 8 pi cubed and so on like that. And that was because of these K's involved here. Then this looks like, okay, 4 pi frequency squared V. But there's more than one wave going on. One wave going this way and one wave going this way. One is an electric wave, one is a magnetic wave. So in place of the 4 pi, we have to bump that up to 8 pi. Multiply the 4 times the 2. The last video ended very abruptly, or I should say the last screen. So uh, this thing went on a little bit longer than I expected. So if you want to keep continuing or try to make some sense of it, I'll continue on where I left off on this one.